Hello everyone, we're going to be doing some math real quick. Hi, it's been almost 5 years since my last upload. A lot has changed in 5 years from when I graduated from my undergrad, and now I'm in grad school for physics, doing my PhD, which is pretty cool. And I realized I haven't uploaded to this channel in a while. I was meaning to do so. As a matter of fact, I was meaning to do this video 3 years ago now, but I recorded it, I had it down, and then I just didn't feel like uploading it. Things got kind of busy that summer, and yeah, I ended up backing up that file into a thumb drive, and now I don't know where it is. So we're gonna be starting from scratch. So what better way to warm the channel back up than by doing something that I think is quite fun and rather important and informative, I suppose, but I'm kind of a nerd, so that's why I would say things like that. But today we're going to be solving one of my favorite integrals, and this thing was absolutely mind-boggling to me when I first saw this integral and this derivation. That was quite a few years ago now. But yeah, I hope y'all will enjoy and take something from this video. So as you can tell from the title of the OneNote, we're going to be working on the Gaussian integral. What is that exactly? The integral I from negative infinity to infinity of e to the minus x squared integrated with respect to x. If you take one long, good, hard look at that, you'll quickly realize that there is no elementary antiderivative for this thing. Elementary meaning like sine, cosine, some exponential function, some log function, some polynomial. Yeah, for those who are kind of advanced to know what the error function is, it's not an elementary antiderivative. So anyways, yeah, so how do we do this? Well, first thing I'm going to point out is x here is a dummy variable, meaning you can replace it with anything. I could have called it y, I could have called it w, I could have called it z. You know, if I was feeling funky, I would have called it like lambda or something. You can even put a smiley face there. It's the same thing. It's just a dummy variable. It's replaceable. So what I'm going to say is I'm going to define a new integral, which is the same integral I. All I'm going to do is change the name of the dummy variable that I'm using. This thing will have the same value. It's the same integral, okay? Dummy variable, just like a summation index. So now I have two of the same integral here. What I'm going to do is I'm going to multiply them. I'm going to multiply the two equations together to get, well, I times I on the left side is going to be I squared. Then I have two integrals that I'm multiplying here. One in x and one in y. And sorry if I sound a little bit sick. It's because I'm a little bit sick. So, okay. So what I'm going to also say is these two dummy variables are independent of one another, okay? They don't talk to each other or interact with each other, basically. I'm sure there's a more strict mathematical definition. All the math people, chill out. I'm just a physics guy. But you get the gist. These are independent variables. So there's some theorem in math, I think it's called Fubini's theorem, which says that if you're integrating, if you're multiplying two integrals that are being integrated over basically numbers, okay, you're integrating over a rectangle, which is in this case, the bounds are not functions of x or y, then you can combine those two integrals into a single double integral with the integrands multiplied together. So that's what we're gonna do. Thank you, Fubini, or whoever said that that's the thing. It might be Frobenius. No, not Frobenius. I just took like a math methods class and we tossed his name around. Yeah, I think it's Fubini's theorem. Clock me on that. Comment down below if that's the case. So what I'm going to do is I'm going to use the math convention for writing down double integrals. Basically, inner integral, outer integral. So we have an integral in y from negative infinity to infinity, and then an integral in x over the same bounds. And we have these two guys multiplied together. Dx, dy. So the inner integral symbol with the bounds is corresponding to x. The one on the outside is y. So I see two things, two things with the same base but different exponents. Well, if you go all the way back to algebra, you just have to add the two exponents. So I'm going to do that real quick to clean it up. Integral from negative infinity to infinity in y, integral from negative infinity to infinity in x, e to the minus x squared minus y squared dx dy. And just to clean this up, I'm going to factor out the minus sign in the exponent. Put this in parentheses right here. Okay, now you'll understand why I chose y for the second variable, just so I can be suggestive. Okay, so right now, it looks like we're integrating over the entire Cartesian plane, right? Over the reals in x, over the reals in y. So I don't really know how to progress from here. So what you typically do when you don't know how to progress when integrating is you perform a variable substitution. In single variable calculus, you'd call this like a U substitution. But nonetheless, we're going to do a change in variable. And if you've taken Calc 3 or are taking Calc 3, you'll probably know how to do this. So whenever you're changing variable for a iterative integral, what you do is you have to insert a scale factor into it. This is what you call the Jacobian. This is because if you change from one variable to another, geometrically what you're doing is you're changing from one coordinate system to another coordinate system. And sometimes the units don't scale the same way, which is why you have to compensate by adding in this Jacobian factor. So those of y'all in Calc 3 that are wondering, why do I need this random determinant thing? That's why, to make sure the units work out and so they scale correctly. So I'm going to perform the following variable substitution or variable transformation, whatever. I'm going to say x is equal to some variable r times the cosine of some other variable phi. Phi to denote the azimuthal angle in the xy plane. So what we're doing is we're making a transformation from Cartesian coordinates to polar coordinates, where r, I'm going to define what these variables are. What is it with the variable and then me using the... Anyways, I'm going to define what r is in a second. I'm going to define what phi is in a second. So that's x, and y will be, well, r times the sine of some angle phi. Here, r is greater than or equal to 0, and phi is within the following interval from 0 to 2 pi. Okay, so now you understand why I chose y, because I wanted to be very suggestive when I perform this transformation. It's going to make a little bit more sense that, okay, we're transforming to a polar coordinate system. So why did I do that? Check this out. So first thing I want you to notice, if I do x squared plus y squared using our new variables, this is r squared cosine squared of phi plus r squared sine squared of phi. I can factor out the r squared, and Pythagorean trig identity, boom, cosine squared phi plus sine squared of phi is going to be equal to 1. So this is just r squared. Check that out. So now let me rewrite the integral. So we have I squared is equal to some double integral. Now I don't know what the new bounds are because we've changed coordinate systems. I need to check the area that we're integrating over. So we'll just call it A of e to the minus x squared plus y squared, r squared, times the scale factor, the magnitude of the Jacobian determinant is what this is called. That thing is a matrix of partial derivatives times dr d phi. So just kind of from a physics standpoint, to talk about this determinant once again. So the units of phi, well, radians are actually a natural unit, so it's just one, no units. dr has units of length, which tells you that this Jacobian determinant has to have units of length as well, because we're integrating over an area. So if you're a kind of a units kind of guy, you'll appreciate that. Okay, so what exactly is this Jacobian determinant? We're going to evaluate it right now. So this is a determinant of partial derivatives. Namely, in this case, how I remember this is basically your old variables. Just take a gradient with the things you're differentiating in the gradient with respect to the new variables. Probably doesn't make a lot of sense. I'll just write it down. dx, dr, dx, d phi. You see how that's like kind of a gradient? You're taking the gradient with respect to the new variables of the old variables. Down here, you guessed it, dy, dr, dy, d phi. So let's calculate some partial derivatives. So partial x, partial r. Okay, let's look at this. Differentiating that with respect to r, we just get cosine of phi. dx d phi, well, the r gets away, but the cosine of phi becomes a minus sine of phi. Then dy dr, again, the r is basically annihilated by the derivative. It's a fun word to use. Sine of phi, and last but not least, dy d phi is r cosine of phi. Okay. Just so I make sure I say this, I'm not sure if I said it earlier. The r is supposed to be like the radial length, and then the phi is the azimuthal angle in the xy plane. Yeah, some of you math people might like, why do you call it theta? It's because in physics, we call theta the polar angle, which is the angle subtended from the z-axis to wherever your point is in spherical coordinates. But that thing in the xy plane, that is phi to me. So that's why I'm using phi. So if I put all these things down, our Jacobian determinant is thus, okay, partial x, partial r, cosine of phi. Partial x, partial phi is minus r sine of phi. Partial y, partial r is sine of phi. And partial y, partial phi is r cosine of phi. So if you take the determinant of a 2x2 matrix, what you do is multiply these two together. So we have r cosine squared of phi minus these two things multiplied together right here. So minus r sine squared of phi. Minus and a minus is a plus, which tells me after factoring out the common factor of r, our Jacobian determinant is nothing other than just r, which has units of length, as we predicted earlier. Okay, so if I substitute that in, you notice that there's absolute value signs. So if I take the absolute value of this, nothing's going to change because r is already greater than or equal to 0. So this is still r. Okay, next, let's take care of our bounds. So what are the bounds of our new integral? So here in the original integral, this one right here, not that, this one, we're integrating over R2, okay? The real is in 2 dimensions, the entirety of the xy plane. How do we integrate that in polar coordinates? Well, what you do is you basically have, if my shoulder here is the origin, you basically have your radial length first, r specifying the first coordinate, and then phi specifying how far you turn around. You subtend if this is the x-axis. So to cover the entirety of, say this is the xy plane right here, this wall, my shoulder is the origin, well, you have to basically extend this radial length all the way to infinity. So let r go from 0 all the way to infinity. And then not only that, you have to basically let this infinitely long arm here sweep around the entirety of the xy plane all the way around 2 pi. So if you can picture that in your head, basically extend a vector all the way out to infinity. This is the origin, basically a line, right? Letting r go from 0 to infinity, and then you subtend 2 pi, so you make one full rotation. And that's how you cover the entirety of the xy plane. I want you to visualize this because this really helps you internalize what we're doing here to the limits. So basically, like r, go from 0 to infinity, and then sweep that all the way around 2 pi. So in other words, our new area, A, is the set of all points r phi such that r goes from 0 all the way to infinity, and phi subtends one full rotation. It goes from 0 to 2 pi. So if I put that down in my bounds, we're going to have I squared is equal to, first set of bounds is going to be in phi. So double integral, first set of limits 0 to 2 pi, second set of limits 0 to infinity of e to the minus r squared, absolute value of our Jacobian is just r, dr d phi. Now, since our limits of integration here are once again just numbers, what we can do is do that, who is it? Fabini, I think. And we have a multiplication of two integrands here, and we can kind of just break it up into two integrals. So instead of having this double integral, I can turn this into a product of two independent integrals. So what I'm going to do is I'm going to put the phi integral in front, and then the radial integral, the r integral, second. Meaning we have an integral from 0 to 2 pi in phi, and then the remaining integral, r e to the minus r squared dr. I can go ahead and integrate that phi integral pretty quickly. This is just going to be, well, antiderivative of 1 is just phi evaluated from 0 to 2 pi, which, when you evaluate this upper bounds minus lower bounds, so this is just really just 2 pi. And then we have this integral here, 0 to infinity r minus r squared dr. And what do you know? I think anybody in Calc 1 can certainly manage that integral, which is what we're going to do. So I'm going to call it J, I guess. And we'll work it out separately. Here we can perform yet another variable transformation, more commonly known as a U substitution because it's a single variable. So let U be equal to, let's say minus r squared. That's one way to do it. You could also just do r squared. But I kind of want to see what happens here. If I differentiate both sides, we'll have du is equal to minus 2r dr. Meaning that du divided by negative 2 is equal to r dr. I see this r dr right here. I'll replace that by du over negative 2. And let's take a look at our bounds. What are our bounds going to be? So when r is equal to 0, r squared is still 0, times the minus sign is just still 0. So our lower bound is yet going to be, once again, 0. And then when we let r go to infinity, what's going to happen here is this r squared is going to go to infinity, but the negative sign is going to make it go the other way. So u is going to tend to negative infinity. So our upper bound here is going to be negative infinity. Oh, that's kind of weird. And so, okay, I see this r dr right here. I'm just going to replace it by a du over minus 2. And I have this e to the minus r squared. Well, that is just simply e to the u. And then the r dr is going to become a minus du over 2. I take that minus sign and I stick it into the integral sign so I can flip the bounds. I'm going to extract the the positive 1/2 and bring it outside the integral just to make things a little bit cleaner. So we have an integral from negative infinity to 0 of e to the u du. Everyone's favorite function to differentiate, integrate, because it stays exactly the same. So integral of e to the u is just e to the u. Evaluated from negative infinity to 0. Okay, when u is 0, e is going to become 1. Sorry, my fridge just like turned on. It does that when it's like cooling down. It kind of scared me. And then, so anyways, back to the integral. Upper limit, e to the 0 is just 1. The lower limit, when u tends to negative infinity, that's going to suppress the exponential. It's going to bring it all the way down to 0. So really, this is just, well, 1/2 times 1 minus 0, which is just 1/2 times 1, which is just 1/2. Cool. Okay. So when I plug that back into my original integral, the I squared stuff, I'm going to have 2 pi times 1/2. And 2 pi times 1/2, last I checked, is nothing other than pi. Isn't that so cool? Like, you do all that work and then it's like, oh my gosh, it's this, very important constant. It's popping up everywhere, this thing related to circles for some reason is, in this integral. So we're not done yet. We have one last step. So since this is I squared, well, we can just take the square root and we'll have, at the end of the day, I, which is equal to the integral from negative infinity to infinity of e to the minus x squared integrated with respect to x. That is equal to the square root of pi. Wow, isn't that satisfying? I don't know, maybe I'm just weird, but I think that's pretty satisfying. So just to kind of marvel at this result a little bit, this is a pretty important integral because actually this function is a probability distribution. It's called the Gaussian distribution. I believe this is actually the normal distribution. It's got a mean of 0 and a standard deviation of 1, I think. Don't clock me on that though. But this is a pretty important probability distribution. Yeah, it's pretty ubiquitous. I know it's kind of strange for me to talk about this, but I'm sure you can find someone who does like STEM stuff and they'll be using this distribution, whatever they're doing. In physics, this pops up in statistical mechanics. It's in the Maxwell-Boltzmann distribution, which basically is like a distribution of speeds of molecules within a gas. Yeah, it's kind of, that distribution kind of explains why if you have like water on the road, like in a pothole or something, why it eventually evaporates. Because at least according to, thermodynamics or, your chemistry or whatever, whenever, water can only evaporate when it's boiling, at boiling temperature, 100 degrees centigrade. And it's not boiling outside. That is way too hot. So where does all of that water go? Assuming the road is not, permeable or has like negligible porosity. Yeah, so that's pretty cool. That's also pretty important in the water cycle. So you can kind of think that this guy is related to the water cycle, which is pretty cool. Because, yeah, if the water cycle wasn't a thing, if water really had to boil for it to evaporate, it wouldn't rain and then we'd basically be like all dead. So, yeah, pretty important stuff. Anyways, I hope you all enjoyed the video. I enjoyed making this. It's been a long time. Yeah, and I guess see y'all in the next one. Peace.